Ouais.
Vous avez mis 20, 20, 21.
Comment?
C'est marqué MECA 507, 20, 21.
Ouais.
Vous avez fait une réunion Teams?
Comment?
Il y a une réunion Teams en cours?
Ah, c'est possible qu'un étudiant l'ait lancé, hein. C'est bon? Et il y en a un qui peut se mettre sur l'équipe 507 de Teams et regarder, voir si c'est bien ce qu'on espère voir.
Moi, je dois aller sur le lien YouTube pour regarder.
Oui, ou sur le lien YouTube.
Ce que je peux faire, par contre, c'est rejoindre le groupe. Si jamais quelqu'un a envie de quelque chose, est-ce que vous pouvez leur dire d'aller sur le lien Teams?
Ah, ben ils savent que c'est sur Teams. Hein.
Il y a 26 participants.
Il devrait en avoir 50 normalement. 26, donc ça veut dire que les gens de la KU Leuven, ils vont sûrement avoir quelques difficultés à se connecter. Parce qu'ils ne sont pas sur la plateforme USB, donc il leur faut sûrement un peu de temps pour trouver comment faire. Mais si tu en as 26, ça veut déjà dire qu'il y en a une dizaine qui ont trouvé, donc ça va. C'est bon? On commence? Voilà, ok, on commence. Ok, donc maintenant, il faut se taire évidemment. Tu me dis quand je peux commencer. Okay, so bit strange situation, of course, with this COVID crisis. We will try to do our best to be good and to teach this class in an efficient way. So everything will be streamed live, normally on YouTube, and also we will have a recording. I imagine that one of the ULB students has started the recording. Mr. Bedoya, I'm sure you have started that. So let's start. So how will this course be organized? So we have always 4 hours and a half on Thursday afternoon and Friday afternoon. I think everything will be streamed, or let's say online, as we say now, even until the end of December. So 4 hours and a half on Thursday and Friday. It will be roughly organized like this: 3 hours of theory until 4:15, 4:20, and then starting at 4:30 you will have exercises with 2 of my assistants, Joël Vinquet and Mariano Di Matteo. They will take you in charge today already from about 4:30. With exercises, I mean you will do exercises with calculations. Computing the cycles, computing the thermodynamic values, computing the speeds, the thrust, the forces, everything that we will see. So these are real exercises, not labs, okay? And during the theory, so it will be organized roughly so that we see the theory, and then you have 1 hour and a half of exercises related to this theory. And this is about organized always like this. So exercises, same theory with a theory and same theory on exercises, always like this during about 6 weeks, so about 12 times. I think we have in fact 13 times. I have also left on the UV, and I will do the same on KU Loket for KU Leuven students, the notes of the first part. What do I name first part? So, in fact, this course is organized, roughly speaking, into 2 big parts. So, we could summarize the course like this. 2 big parts, both on aero engines, of course. This is aircraft propulsion, so we will speak about aero engines. And the first one on aero engines will be on cycles. So we will study the different cycles. We can say thermodynamic cycles, but it will be more, in our case, an architecture that we will define, not so much a thermodynamic cycle. And we will study the different cycles that are still today existing and that have existed in the past, let's say from an historical point of view also. And the second part, that will be in fact the third one, because you will see there will be an intermediate part. This is a part on the components. So after having studied the cycles, where we are not putting so much details on the different components you have inside the engine, we will go through the different components from the entrance to the exit. So going into the details of each components and trying to understand what are the challenge in these different components and the most important questions, the most important physical parameters taking place. You see that I've put in the middle of these 2 parts a third one, which is on what I call the working points and the working lines. So we will need at a certain moment to look at the engine from a, as we say in English, an helicopter point of view. That means not looking too much at what's happening in the compressor, what's happening in the turbine, what's happening in the combustion chamber. No, looking at the engine as a whole. And so we will look at the engine working point and working points. And when you are assembling points, you have a line. So we will define a working line. And we will see that there are different working lines. This is also a theory that you could call the study of the steady state lines. The working line or operating line can be also called a steady state line. And there, this is a very important part because it will give us a very clear, let's say, intermediate part between just studying cycles, not looking at so much the components, and the study of the components by seeing the engine as a whole, only an engine. And we will see that we will be able to summarize, let's say, all components of the engine on just one chart, So this could be also called an helicopter view of an engine cycle, of an engine architecture of an engine. And that's why we can say that we will discuss 3 parts, but this one will be very short. It will take us about 1 day, 1 afternoon, whereas the other ones, this is, globally speaking, this is about the ratio of half days that we will have, 6 about the cycles, 1 about the helicopter view, the steady state line theory, and 6 about the components, okay? If, because I know that students are quite interested by exams, so marks, the points, in fact, it will be very similar to one afternoon, the exam. In an afternoon, we have a part on theory and we have a part on exercises. And the exam, it will be the same. So it will be 50-50, 1 or 2 or 3 exercises on paper that you deliver at the end. This year, I don't know exactly how it will be organized, if it will be in a room or if it will be online, I don't know exactly, but you are receiving an exercise with some figures, with some tables, with some data, and you solve it and you deliver your sheet at the end. This is the exercise part over 10 points. And then we have an oral exam. An oral exam with me, where normally you have preparation time. Of course, if this is online, I don't know how we will organize that. We will see. This is in January. We will see the situation at that time. This exam of theory, so oral exam, you take a question from a list. So I will send you at a certain moment a list with, there were 18 questions in the past. I think this year there will be 19, because something I was discussing could certainly become a question related to the huge discussion taking place in the world of aeronautics related to that. I will explain you that later. So there is a list of questions. So you receive this list. Now 18 questions in the past, maybe this year 19. And so you have the questions, you can prepare them, and at the exam you take one of these 19 questions. There is a table, or let's say a list of questions, and you take one of these questions. So you know the questions in advance, but in fact these questions are, let's say, covering the whole material, globally speaking, okay? So let's start with the study of aero engine cycles. And in fact, I'm starting this class not by speaking about aero engine cycles, but by speaking about what I call, I can go there, what I call the basic gas turbine cycle. This is the first cycle that we will study, a GTE, a gas turbine engine, and the most basic one, the easiest one, the simplest one, if you want. And this is useful because, first, there are applications of this very easy gas turbine engine. Second, because we will see that the study of a gas turbine engine on board an aircraft is quite complex. And so starting by studying an engine that is a bit easier, let's say, will certainly help us to gradually increase the complexity of the analysis and of the study and of the equations, okay? And what is in fact the most basic gas turbine engine that we could imagine? So a gas turbine engine, this is based on turbo machines. This is based on a turbine or turbine, if you are English or American. And a turbine, this is driven by a source of energy. So you have a turbine that is normally drawn like this. And at the entrance of this turbine, you must have a high energy flow. This high energy flow, we have seen that in the course of turbo machinery. it can be a high pressure, it can be a high temperature, it can be a combination of the two. It can be also a lot of kinetic energy. There are different ways to have a large energy. And normally, in aircraft engines, at the entrance of a turbine, also for electricity propulsion, it will be a combination of all this. So a high pressure, a high temperature, and a high speed or high kinetic energy. Of course, there is also related with this pressure, related with this temperature, related with this speed, there is also a mass flow rate. M dot dm over dt, which is something in kilo per second, so a mass flow rate. We will never speak here in volumetric flow rate, very rarely, because what's important, this is the mass. Rho will change a lot, so you know that the mass flow rate, this is rho VA, and rho can really change a lot in an aircraft engine, in the compressor, in the turbine, in the combustion chamber. So we speak here normally always in m dot in mass flow rate. And how can you have a large energy flow? There are different ways, of course. You can store energy using compressed air. So this is certainly a solution, but how can you use that in a continuous way? This is impossible because the tank where you are putting the compressed air would become empty very quickly. So it's not possible. So the, let's say, only continuous way to proceed is to have a combustion chamber. Combustion chamber, I'm representing that like this. Today, we will, in the study of the components, really analyze combustion chambers. There is a combustion chamber here. So we will analyze this combustion chamber into the last details later on. But let's say today, we just represent a combustion chamber like a tube. A cylindric tube where we have at the entrance air. So here we have m dot air. We are injecting m dot fuel, and here we have m dot gas. And thanks to the combustion that we will have there, the temperature will increase a lot. You hope that the total pressure will not decrease too much, and so you keep a very high energy flow. The problem is, if you want to do that, if you want to realize a combustion, if you want to burn a fuel together with air, especially in an open combustion chamber like this one, you see it's very different compared with an internal combustion engine. In the cylinder of an internal combustion engine, you have a very small volume. Everything is closed. It's quite easy to realize a combustion. Here, you have a flow at high speed entering here and leaving there, and you need to realize combustion. It's very complicated. We will see how it can be solved, but it will be a real challenge. And so, how can you ensure that you will have, let's say, a good combustion? We will see later on what we call a good combustion. This is by having the right conditions at the entrance. So here at the entrance, you must have the adequate speed, the adequate temperature, and mainly the adequate pressure. So we will reduce the speed because otherwise the flame will blow out. You have an interest of having a rather high temperature in order to have the fuel in the best condition in order to ignite it, maybe to vaporize it if you have a liquid fuel, but mainly you need a pressure. And how can you have a pressure? Again, you could use a tank, but the tank would be empty very quickly. So you need to have a continuous system. And so how can you have a continuous system? By putting here, of course, a compressor. So if you need to have high pressure, what is the best solution to have high pressure? This is to put a compressor. You will say maybe, how can you have a compressor? It's difficult. Yes, it's difficult. Yes, for sure. But this is the only solution to have a continuous system. And how can this compressor be driven? Of course, by the turbine. I will use another color. You have in between here a shaft, of course. This shaft, this is the name that I will very often use, is sometimes also called a spool. I will define exactly what is the difference between a shaft and a spool later on. And so what do you have? You see how the system is working. I have a high energy flow. This high energy flow will flow in a turbine. The turbine is generating work, transformed, because at a certain distance from the shaft, into a torque. This is the torque, very, very important parameter. Always people are speaking in power, but this is ridiculous. We need to speak in torque, because everything is starting rotating thanks to torque. C'est bon? So you create a torque. This torque will give you a rotational speed. So it gives us a power, and this is driving the compressor. The compressor on its turn is increasing the pressure. By increasing the pressure, you go to the combustion chamber, you have the adequate pressure, you inject the fuel, you mix the fuel and the air, you ignite the mixture, you increase the temperature, and you see that you have this cycle, high energy, work, torque, pressure, ignition, and you have, let's say, a cycle that is going into this direction. Of course, if you take the flow is going, let's say, in this direction, going through the compressor, then going through the combustion chamber, and then going through the turbine. Entering at, let's say, low temperature, here you have certainly a low temperature, and leaving the system with a high temperature, because you will not be able to recover the full temperature, the full energy you have in the turbine. And in fact, it depends, of course, on the system. It's not maybe needed to expand everything, the oil pressure you have in the turbine, because maybe you want a high power, high work, high energy in the flow here behind the turbine. Okay? And this is what we will call the basic gas turbine engine. A very simple system with a compressor, a combustion chamber, and a turbine. Of course, you need to guide the flow to go outwards. So here you will need to put a nozzle like this, or maybe if you are in a ship, a nozzle like this, that is bringing the flow out of the system. But we are not putting too much importance on that because it's not looking like a mandatory system. Okay? And so this nozzle that we have here, in a first assumption, we do not need to take that into account. Most probably, you will need also to guide the flow towards the entrance of the compressor. So you will need to have what we will call later on an inlet. Again, here we will not put really the accent on the existence, on the presence of this intake, and it will be something that will be, let's say, neglected, that will be assumed not having too much importance, and we will come back later on on the influence that this inlet, that this intake can have. So, and that's why we call that a basic gas turbine engine cycle, because this is the most simple cycle that we could imagine. We do not consider the inlet, we do not consider the nozzle, and we are, let's say, just considering the components that are the most important, that are absolutely necessary in a gas turbine engine. Is it feasible? Is it not a too large assumption to consider that? This is certainly what you can imagine when you have here a speed that is equal to 0. So when the aircraft, when the air, you can say that A, this is the air, or that you can say that A, this is the aircraft. When you have a static application, this is what we will use as a terminology, static application, that we will very often just note S later on, means that the system is not moving. Maybe that the system is moving at very low speed. Let's say if you take a ship, for example, cruising at 10 knots or at 15 knots, you can certainly consider that this is cruising at a very low speed. And if you are considering that you have a very low speed, we can certainly say that we do not need to consider something before the entrance of the compressor. The compressor will suck the air from the environment that is at a speed about equal to 0. And of course, when I'm speaking about the A, it can also be called the ambient conditions. A can be for air, A can be for aircraft, A can be for ambient. You will need, of course, to consider also the two other very important ambient conditions that are the temperature, TA, and the pressure, PA. Both of them are defining rho A, which is equal to PA divided by RTA. We could certainly also speak about the relative humidity. This is something that we could also consider, but in aeronautics, we are not so often speaking about the relative humidity. In terrestrial, in static applications for electricity generation, we will speak about the relative humidity, but in aircraft engines, not so much. Why? This is because where the aircraft are flying in cruise, the relative humidity is extremely small, except when they are flying through a cloud. But in normal flying conditions, the relative humidity is very, very small when you are at 10, 11, 12, 13 kilometers altitude. Okay? And so static conditions, keep that in mind. That means that VA is equal to 0. Okay? Now, what is, so you see the basic gas turbine cycle, this is, let's say, the lowest number of components. Compressor, combustion chamber, turbine. Inlet later on, exhaust nozzle later on. There is a second, let's say, assumption or second simplification that we will consider when discussing about the basic gas turbine engine. This is the fact that we will say that the total components will be equal to the static components. What do I mean by that? The total pressure, the static pressure, they will be considered as the same. The total temperature and the static temperature also considered to be the same. Okay? Is it important? Yes, because when you cannot consider that they are the same, you will need to compute the total temperature and the static temperature. You will need to compute the total pressure and the static pressure. So there is indeed a difference. Okay? Here, by considering that, we are simplifying all the equations, all the questions we can have when we will solve the different situations of the fluid by saying that the total and the static conditions are the same. Are the same where? Where are they the same? You see that we have discussed a compressor, a combustion chamber, and a turbine. And in fact, each component will be defined by an entrance and an exhaust. The exit of one component being the entrance of the next one. Here, this is the section that we will call 1, of course. You are entering into a system with the section 1, and you are leaving with the section 2. So I mean, when I write something like this, that I have this. I do not want to say that TT1 is equal to TT2. I just want to speak about the, in a given section, that the static and the total parameters are the same. And after that, I will have as a third section the exit of the combustion chamber or entrance of the turbine, and as a fourth section, the exit of the turbine. And you see that in this basic gas turbine engine, we will have only 4 sections to compute, 1, 2, 3, 4, and in each of these sections, only 1 temperature and 1 pressure. And so, let's say, compared to the cycles that we will see later on, this is reducing the number of parameters that we need to compute by a ratio at least 2, because static and total, but much more than 2, most probably 3 or even 4 times more in the cycles that we will study later on. And of course, you could also represent this cycle on a TS diagram or an enthalpy, entropy diagram. Of course, speaking in total elements, as we have said that the static and the total elements were the same, and you start from the point 1, so which is the entrance of the compressor, and of course, by the assumptions that we have considered, you can also say that the point 1 is the point A, because in the point 1 you will have that the temperature will be equal to TA, T1 is equal to TA, you will have that P1 is equal to PA, or better to say that PT1 is equal to PA and TT1 is equal to TA. So you will have that TT1 will be equal to TA, and you will have that PT1 is equal to PA. But in fact, TA is also equal to TTA, because we have said that VA is equal to 0, and PA is also equal to PTA, as we have said that VA is equal to 0, VA equal to 0, or NA equal to 0, the Mach number that is equal to VA divided by the speed of sound. And so you see that by considering the different assumptions that I have enumerated, we will have a first point at the entrance of our compressor that is very easy to define. You just measure the outside air temperature, this TA, this is very often what I will call the OAT, the outside air temperature. This is a jargon of aeronautics. And this is the temperature TT1 at the entrance of your compressor. And you have also the PT1 by measuring with a barometer the atmospheric pressure. If you would have a nice entropic flow, you would arrive along a vertical line at the exit of your compressor. Exit of your compressor that is at a total pressure PT2. How can you define that? PT2 is equal to the pressure ratio multiplied by PT1. Very easy. of course, we are not arriving in this pressure in an isentropic way. We are not arriving vertically in the point 2i. We will arrive in the point 2, that is here. We will need to see the difference between the point 2 and the point 2i. And after that, you are flowing inside a combustion chamber, so going very high in temperature with a small pressure loss, because there are some friction losses, fluid against fluid, fluid against the walls inside the combustion chamber. So you will arrive at PT3, that is slightly lower than PT2. What is slightly? We will define that later on. And reaching a very high temperature that we call the TT3, that is the, let's say, highest temperature defined in a section. So it's not the highest temperature we have in a cycle. I will discuss that later on, but in a section, this is the highest temperature. And from there, you will expand. You could expand in an isentropic way in the turbine, or you will expand in a real way, so in a non-isentropic way, so with an increase of the entropy like this. And what do you need to represent? What do you need to represent? You need to represent here PA, which is also equal to PTA, which is also equal to PT1. And here you will expand. You will expand down to what? So you need to look at this. Look at this. If you extend the PA iso pressure curve, you see that you can locate, you can position the exit of the turbine related to PA. And at the exit of the turbine, you must be at least equal to PA. Otherwise, here you have PA, the P atmospheric here outside. You see the exit of the turbine must be at a slightly higher pressure compared to PA, other the flow will never leave the system, will never leave the pipe, will never leave, I don't know what you can call at the exit of your turbine. And so you must be higher than the PA, that is the extension of this one, the same isobar curve. And so where are you arriving? It depends, it depends. So you will arrive, let's say, at a value like this, in an isentropic way or in a non-isentropic way. And what do we see? What do we see? We see that if this pressure P4 is high or very high compared to PA, what do we see? Depending on where you arrive, I will show you two cases, just slightly higher than PA, P4 just slightly higher than PA, or much higher, so P4 much higher, here P4 is just slightly higher than PA, or P4 much higher. What do you see? The higher the value of P4, the higher the value of T4. You see, very important. If we are not able to expand the flow to the minimum pressure, so to have the largest expansion of the flow, what will be the result? You have a higher temperature. Is it good? Not good? It's not good, of course, because your cycle is intended to do what? Your cycle is intended to drive the compressor and to give energy here, but not energy under the form of temperature. because your system doesn't need to warm up the atmosphere. So this is not a good solution to have the 0.4 at this position. You must have the 0.4 at the lowest possible position compared to the atmospheric pressure. That means just slightly higher. This is something you need to keep in mind. We see that already now, just by looking after half an hour to the cycle. Be careful, the way you expand the flow in the turbine will have an influence on the quality of your cycle. And the cycle arriving here is much better than the cycle arriving there, because the cycle here is eating up the atmosphere much more than the cycle that you have here. Okay? Of course, we can also think about what is the cycle exactly doing. So you can have a large energy here, and you will use this flow to do something. I don't know what can be the objective. Another solution is to say, I will have here a very low energy flow, and to expand more in my turbine. I expand more in my turbine. And what do I do with that? I have more power here. The power generated by my turbine is higher than the power needed by the compressor. And if I have a surplus of efficiency, of energy, of power, what will I do? I will drive here a load. And you see that this basic gas turbine cycle can be used, let's say, in aeronautical application with a high energy, and you will do something with this flow. Or it can be used in non-aeronautical application with a very low energy here behind, just able to leave the system. But if you have a low energy there, and if the energy was the same here, you extend the turbine and you drive a load that is here. And so you see that this cycle is also a cycle to generate, let's say, work on a load. It's a cycle that can drive a load. What type of load? Very often we speak about electric generator. And so this cycle is also the cycle used to generate electricity. So you have already heard that a few times, I imagine, when we speak today about the nuclear power stations, the fact that we do not have enough electricity at some moments during the winter. Some people say it's not a problem, we will switch on the combined cycles. In fact, these combined cycles are based on a gas turbine in the middle of the system. It's a bit more complex than that. And this gas turbine is just driving an electricity generator. So in order to produce electricity for the grid. And so, in fact, in this first lesson, and also a bit tomorrow, I'm speaking not so much about aero engines. I'm speaking about something that is the basis of an aero engine, but that is also the basis of electricity generation. And this is the gas turbine engine. Of course, the load can be something else here. It can be an electric generator. It can be the wheels of a car. It can be the wheels of a Nassau tank. It can be also something in order to drive the propeller of a ship. It can be also the rotor of an helicopter. There are so many applications, but always with this very basic gas turbine engine. And it looks like extremely simple, of course, and so attractive. But the system is very complex to build and to define. Why? This is because in order to exist, in order to have this cycle, what do you need to have? You need to have that the PIT is at least equal to the PIC. So the power generated by the turbine must be at least equal to the power absorbed by the compressor. And this is very complicated. In order to have this, you need two things. You need to have a TT3 that is extremely high. So the temperature you have there must be extremely high. This is what will make that the power delivered present of the shaft on the shaft of the turbine will increase. And this is extremely complex because it requires very advanced materials or technology in order to be able to work in these high temperatures. At least, let's say, something like 1000 Celsius order of magnitude, in order to have a very easy order of magnitude in mind. Okay? But the second thing is that the PIC cannot become too large. And in order to have a rather moderate, not too large power absorbed by the compressor, what do you need to have? You need to have an isentropic efficiency of the compressor that is high. Okay? So that means you must be able to have the adequate shape of the components in the compressor, of the blades, of the vanes. You must have a good material, a good finish of the surface, the roughness of the surface, all, let's say, clearances, all gaps that you have between the rotating part and the non-rotating parts must be small, etc., etc. And these are two challenges from, let's say, a technological point of view. And it took years and years and years to the engineers to improve the turbines from a thermal and mechanical point of view, and to improve the compressors from an efficiency and geometry point of view. And gradually, so the PIT, that was much too low compared to the PIC, the difference has decreased, and at a certain moment it was the same. So then you have a cycle that is delivering no useful power, and at a certain moment you have this balance, and at this moment you have what we need to have, that means a useful power here at the exit. So the difference between these two, the difference between PIT and PIC, this is the useful power, which is, let's say, what the cycle is delivering. And this is not easy at all. It took a long time to the engineers in order to be able to have this unbalance, this positive unbalance between PIT and PIC. Okay? Also, we must certainly speak about the reason why the engineers and the stakeholders have spent so much time to reach this positive unbalance. Because you could say, okay, if it's so difficult, then we stop and we will come back to that within a century when it will be easier to solve. No, there is such a large interest, such a large attractivity in gas turbine engines that they have tried and tried and tried and tried. And what is the so large interest that you have in gas turbine engines? This is the fact that the system is almost frictionless from a point of view metal against metal. So in a gas turbine engine, you have friction between air or gas or fuel with metal. but there is almost no contact metal against metal. That means that the wear in a gas turbine engine, in the engine that we have defined there, is almost zero. So you have an external carter here, you have an external carter there, you have an external carter here, one there, and it makes the link, but there is almost no mechanical contact metal against metal. The only place where you have a contact, this is in the bearings. So you have bearings supporting the shaft. Let's say a ball bearing in order to take some axial loads and radial loads, and cylinder bearings to take the radial loads. This is the only place inside the bearing. So this bearing with the shaft, or this bearing cylinder, there are 10, 12, 11, I don't know how many cylinders. Each of them will be in touch with the inner ring of the bearing and the outer ring of the bearing, the inner ring being the shaft, and the outer ring is here. And this is the only place where you have metal against metal. So, a priori, why have they so much tried to solve this problem that was extremely difficult to solve? Because, a priori, gas turbine engines, they have an infinite life, we could say. Maybe we can say very, very long life. On the contrary, compared with the internal combustion engines, where you have the piston that is frictioning, gliding inside the cylinder, and where you have a lot of contact, metal against metal along the crankshaft and so on. Okay? Now, there is something else that is attractive in gas turbine engines. The first one is the extremely long life, but there is a second very attractive feature in gas turbine engines. This will be the power to mass ratio. This is the engine with the largest power to mass ratio. That means with the largest, what is so called sometimes the specific power. So the specific power is not the power to mass ratio. I will define that later on. But I mean, if you have 1 kilo of material, this is the engine that will give you the largest power available. Or for a given power, because this is very often the power that we consider as a constant, it will be the lightest engine. So this is something you need to keep in mind. Aircraft engines are a technology that is very, very light. The power to mass ratio, what later we will call the specific power, which is not the power to mass ratio, but it's closely related, is very high. We will come back on a clear definition of that, but these are the very attractive points. Almost infinite life and very light system. And if you speak about this for electricity generation, light, it's not so important, because this is a static application. But as soon as you put the system in a driving body, for example an aircraft, then mass, so weight, is becoming extremely important. Okay? Now, what will we need to compute? So, we will always do something very similar. So here, this is the first cycle that we are studying. And we will define other cycles later on, what we will call the turbo shaft, the turbojet, the turbofan, the turboprop, turbofan with after burning, etc., etc. So these are all different cycles, but for each of these cycles, we will always try to follow the same path in the explanation of and the understanding of this cycle. What will we do? We will take an existing engine. So let's take this engine, for example. So you see this engine. This is an existing engine. So you take your measuring systems, you measure all sizes, all pressures, or temperatures, mass flow rates, everything that is existing inside. So you have a sheet of paper and you can see all details of this engine. And I ask you to compute this engine, to compute all pressures, all temperatures, all power, all energies, all consumptions, I don't know what you can imagine. All kinetic energies, everything that you could imagine. So this is what I call an on-design computation. So I compute one working point of the engine. I take a certain PA, a certain TA, and a certain m dot, for example. So, or if you want a certain TIT, sorry, I have not yet defined that, the TT3, and you compute based on all the data you have, the cycle, okay? And of course, we are in a situation where VA is equal to 0, okay? So I give you the engine that I've shown there, all the data, everything, you have everything. So you know the combustion chamber, you know everything. And you decide, you go outside today, you measure PA, you measure TA, VA, it's fixed, and you start the engine, and you go to the working point that I have given you in the data sheet, and you measure the things, and you can compute the cycle. So this is what I call on-design computation. This is, let's say, computation of one working point. And that will help us to understand. So what are we doing? What are the equations? What are the performance? Can I compute P useful here, for example? Can I compute P m dot fuel that I need in order to reach the TT3 that I have there? Okay, it will help us to understand. And then we will have a second step. Step number 2, it will be in order to understand how I could optimize the cycle. So I have all equations, I have all performance, I know how to compute the system. The question is now, how can I optimize the system so that, for example, P useful is maximum? Or I don't know what is minimum, I don't know what can be the objective. Let's say, in order that the efficiency of the engine is increasing. So this is an optimization problem. And the optimization problem is, of course, still at a certain PA, TA, m dot, and VA is equal to 0. And I will try to see what I can change in this cycle in order to have a parameter that is better, efficiency higher, for example. Of course, I cannot explain today what I will try to optimize because I have not yet defined the cycle. And that will help us, for example, to have the efficiency that is maximum. Because everybody can understand an efficiency. We don't know which efficiency, but everybody knows, okay, there is certainly an efficiency I can define. Let's try to have this efficiency maximum. And for example, it will be, because there are not so many parameters in the cycle that I have defined. What are the parameters that I have defined? This is a parameter, and this is a parameter. The rest, I don't have any other parameter. This is the atmosphere. And so you see that if you change this one, you will change the position here. Okay, you may say that you have also the isentropic efficiency of the compressor, but this is technology. It's not a thermodynamic parameter. And you will say also, the loss that you have there, it's also technology. So you see there are only two parameters. This is TT3 and the pressure ratio. And so the optimization problem, it will be to define how do you need to select the pressure ratio and the TT3 in order to optimize what we have not yet defined, but the efficiency. And after that, what will you do? You will define what is in fact your design point. Because you have made an optimization, so you know what is your best point. And this best point, you call it the design point. It's a bit strange because there we have called that on design. We can call that working point computation if you want. This is because it was the only point that we had. But now you can fix the design point. And what will you do afterwards? You will do the most important, I repeat, the most important thing that we need to do with aircraft engines. This is to study off design. Why do I say that this is the most important part? This is because there are so many parameters changing in an aircraft engine, let's say life or operation, that you will be 99.9% of the time in off design. And so you need absolutely to control this off design working of the engine. You need to know if when you go in off design, you are not degrading too much what you have optimized. And what will be the off design things that you have already to check in our basic gas turbine engine? Influence of PA, because we have always considered that it was this PA that we have today outside. But if we are in the summer with a higher PA, if we go with this engine in the Alps, in the mountains, I don't know, PA will change. Also, the same with TA. Maybe also, I come back to that, to a parameter that I have a bit neglected, the relative humidity. It can be something that is also important, even if we are not discussing that so much in aircraft engines. And also, or are you changing the parameters of your design? Because you are not in the design point anymore. You can change the TT3, you can change the pressure ratio. Maybe they are changing together, maybe they are changing independently of each other. How will you change this? And of course, you should also check VA, but here not, because we have considered that VA is equal to 0. And so you see that when you will move to non-basic gas turbine engines, instead of looking in off-design conditions to the change of 1, 2, 3 parameters, you will need to go to 1, 2, 3, 4. So again, complexifying the situation compared to the basic gas turbine engine. And in all cycles that we will study, it will always be the same rationale. Of course, more complex and more complex when you increase the complexity of the cycle. But always try to compute one working point, understand how this engine must be calculated, what this engine is doing, how can you define the performance parameters. Second step, this is, okay, I have defined the performance parameters, how can I improve one or two or three or four, I don't know, of these performance parameters. This is the optimization problem, and it helps you to define your best operating point that you can call the design point. And after that, you will go to the most important point, which is of design computation. And in fact, you could say almost that the design point is not so important, because we will be in 99% of the time outside of the design point, outside of the design operations. So this design point is not so important. And indeed, this is true, because very often for an air engine, yes, there are people who know what is the design point, the engineers who made the very first design, but it's something that has disappeared. Nobody knows anymore. But because it's not so important. In fact, it is important somewhere, because you don't know exactly where is this design point, but the selection of the design point must be in some directions, so that you will not change too much the performance of design. If you select a bad design point, the off-design performance will be too bad. But the precise place, definition of the design point, it's not so important. It's there around, but not critically important. But if it's wrongly selected, the off-design computations, the off-design performance will be bad. And so you need to keep that in mind, always a three-step approach: one point calculation, optimization, definition of this design point that is a bit vague, not very well known, and mainly the off-design. And the off-design, of course, the off-design study requests a very good knowledge of the engine, a very good knowledge of the engine. Okay? I propose that we take a short break now. So if you want to take a coffee or a beer, as you are at home, you are not driving, so you can drink a beer. And what will we do just after the break? We will do this, the undesign computation. That means I will take a cycle and I will compute the cycle. Like I buy an engine and I reproduce everything that I see inside so that I understand what I have in front of me, and I can, of course, if I have a test bench, I can measure these parameters and check if my model is corresponding to the experimental values I get. Okay? And after that, we will define the parameters that we will try to optimize, and after that, we will go to the off-design. Always for this basic gas turbine engine, that will be the foundation, the basis of all cycles that we will use later on in aero engines. And this basic gas turbine engine, as I said, is also the basis of gas turbine engines that are used to produce electricity for the grid at some moments of the day or at some moments of the year on top of the nuclear power stations. You have a lot of these gas turbine engines in industry, especially in the Flanders. In the Flanders, you have a lot of industry having gas turbine engines inside their walls to produce their own electricity, and then they are selling the surplus of electricity they have to the grid. And this is a basic gas turbine engine as the one that I have described. See, another advantage of the gas turbine engine that I have not mentioned, a third one here, that is very quick to start. So this is a system that can be started very, very quickly. And this is certainly, of course, a huge advantage if you need, at a certain moment, I need electricity. So you start the system, and a few tenths of seconds later, you are already putting electricity on the grid. And this is due to the fact that we have low friction, because we can start the system with, thanks to the very low friction metal to metal, almost instantaneously. Okay? So, let's see you in a few minutes.